All right. Yeah. Uh, hey everyone. Thank you for joining us today um, at this late time on a Thursday night. Just before I start, I just want to introduce myself. My name is Sahil Panjwani. I am an undergrad senior, uh, probably going to do my master's 4+1 over here, and I am an aspiring researcher at the intersection of remote sensing and quantum computing. So coming back to today's topic, I'm very excited to present intro to hybrid architectures to you guys. And I'm curious, like when you think of hybrid architectures, like what kind of pops up in your mind, if anyone wants to volunteer? Okay. Anyone else? Well, something that popped up in my head, I think one that's very common as well is multimodal, right? Multimodal or multimodality is what we think of when we think of hybrid architectures. Well, a big part of today's presentation is going to focus on that, including the hands-on. But apart from that, I'm also going to tell you all about what the last line over there is showing us, which is integration as the new frontier of machine learning. So I'm going to talk about a lot of other paradigms as well, which you might not think of when you think of hybrid architectures. So um, the the wordings that I'm going to use or like for the next few slides is going to be blocks. So you're going to see that a lot in the next few slides. So just bear with me if that becomes repetitive. So moving on to the first block that I'm going to talk about today, which is the spatial representation block. So this consists of uh, a model which deals with any type of spatial or geometrical data. This can include images, point clouds, or meshes. So we take in these raw spatial data, the flow like goes like that. We take in the raw spatial data, pass it through a neural net which acts like a feature extractor, like CNNs, for example, and create these meaningful feature representations that you can use for downstream tasks like classification. So if you look at the diagram over there that I have, you can see that I have an image of a dog, right? So this image is then passed through a CNN and some intermediate features are extracted, which you can see in the activation maps over there that highlight the spatial regions that the network is focusing on for its decisions. So essentially, this is exactly what a spatial representation block does. It predicts patterns from images in important regions that we want to focus on. So in short, compressing raw pixels into geometrical and pattern-aware features that can be used for any of our objectives. Now, if I talk about the three key strengths of this block, that is pattern identification, like I told you. So like this is repeated patterns like edges or textures or boundaries of an object. This is what I'm talking about when I say of pattern identification. When I say spatial invariance, I'm talking about these geometrical structures, or sorry, like these shifts or rotations and scaling. Like for example, if we have an image of a dog, right? If we scale it, slightly reduce it, or like enlarge it, or like shift it towards like left or right, the CNN is still able to predict the the object with same accuracy as you would if it's not scaled. Then the third is geometrically aware. So spatial models can encode relationships between shapes and distances between objects, as well as the structures itself. So this is especially important in 3D tasks like robotics or maps, where the arrangement and geometry of the environment matter as much as the object themselves. So this is the first block that I want to talk about. Moving on, the next is the temporal block. So this is the block that focuses on data that unfolds over time. And unlike what we saw in the spatial block just now, which captures geometry and structure in space, here the main challenge is modeling order, sequence, and dependencies across time steps. So over here, if you see the flow, it takes in sequential data as input, passes it through a neural net like a RNN or an LSTM, and then outputs temporal feature representations. If you see at the example over here, you see video frames being processed sequentially. Uh, and you have also temporal attention and recurrent gates over there, which basically are applied to learn exactly at what point do they see the object in the frame. And not only that, but also the context with the whole sequence altogether. So this is basically the idea of temporal models, that they look at how things evolve over time rather than just focusing on a single snapshot. Now, if you talk about the strengths of this block, I already kind of hinted at sequential modeling. So the ability to capture order and progression of events. The other is long range context. So modern temporal models, especially attention based ones, can connect information across long term contexts. So this can include like remembering the first scene of a movie and remembering that when you're interpreting the last scene of a movie, if you're predicting something. The other key strength is forecasting. So temporal models, they don't only just predict like what has happened, like we saw in this example, they can also predict what's going to happen based on past context. So that is the three key strengths of this block. Moving on, the next is what I call the reinforcement block. And over here, we're not just focusing on the data, but we're like passively, but also focusing it in like an interactive environment. So here we have an agent that observes the state of the environment, takes an action, and then receives a reward. And over time, the agent learns a policy, which basically is a strategy to maximize the said rewards. So if you see this example over here, the robot is in an environment where it's tasked with like reaching that target, which is a soda can. The vision module provides input images, and then the RL module decides what action to take based on the outcome. So the environment returns a new state and a reward at the same time. And this loop continues, which allows the agent to gradually improve its behavior. So you can see that the RL is all about continuous interaction and feedback rather than what we just saw with temporal and spatial, where it's like passive analyzing data. Just quickly going over the strengths of this block, it's self-improving. So through trial and error, the agent learns from its own experience, and you don't require explicit labels like you might need in like supervised learning in other areas. Long-term optimization. So it doesn't just optimize immediate outcomes, but also learn strategies. So a cumulative reward over time kind of situation. And then finally, adaptive control. So RL agents can adapt their policy to changing environments as well. If some sort of dynamic shifts, like new obstacles appearing, the agent can still adjust its behavior accordingly. This is something that you might not see in like supervised learning, for example, right? Next, we move on to symbolic or rule-based AI, right? And this is like from an earlier era of AI research, but it's still very relevant in like many applications nowadays. It's all about logic, rules, and reasoning. So instead of like raw data that we had before, we are focusing on just rules and allowing the model to reason based on them. So you can see in that block diagram over here that you feed those rules into a neural net, like a graph neural net or a Bayesian probabilistic neural network. And then that reason engine applies an if-then logic to make decisions or conclusions, like it says. So if you talk about the strengths of the model, actually, let's quickly go over this example over here to like really reinforce that point. This is a graph of a moving car. So this diagram shows a very simple rule-based flow. If an handbrake is activated, then do nothing. If it's not, then accelerate. And that is how the logic is built. So going over the strengths, the first strength is explicit reasoning. So symbolic systems can follow well-defined rules step by step. So like you saw, like applying logics or constraints to reach a conclusion. Second is explainability. It's all out over here and transparent. You can exactly map at what step, what action what actions you can take, right? And then finally, compositionality. So like symbolic AI is naturally good at combining smaller pieces of knowledge and building larger and like tackling larger complex problems. Because there are like very defined blocks like this, you can really accumulate them and tackle a very complex problem. And this is why I call this the reasoning block. So because unlike the others, its true strength lies in making reasons explicit, explainable, and composition. Lastly, we have the physics-informed ML block. So this is different from others in a way where, just like symbolic, where we're not relying on data, we're also relying with data, we're also bringing in governing laws of physics or like scientific knowledge. So over here, like the inputs become that raw data as well as partial differential equations and some boundary conditions. And then the neural network uses these constraints to give some predictions. So these are generally used in simulation applications. So like you can also see the example over there of fluid dynamics, where how deformations are constrained by physics, basically, and you solve a physics equation to simulate like the predicted kind of shape of that human being over there. So the key thing over here is that since it's heavily defined by these knowledge rules, you don't really need a lot of data to like make these simulations that you might need with like a CAD model or like some other kind of 3D representation, right? So that is the main strength of these blocks over here. Uh, I talked about data efficiency, leveraging priors also. So like these priors are facts, right? So we know that this is the kind of prediction or closely estimate this is the kind of prediction that we might have using that. So that is the second thing. And then trustworthy. That also like goes into like scientific knowledge. We can explain these systems to any stakeholders if we want, because we know that it's not a black box like a normal neural net. So you might think that like after all of these blocks, actually like before I go into this slide, any questions on the blocks itself? Yeah, they're still applicable in language models. So like the textual block that you said, like temporal block that you saw, over there you can give it sequence of text, for example, or like an RNN takes a text input as well, right? So it can also be done using that. Yeah. All right. So moving forward, you see that I have gone over strengths, like unique strengths of each of these blocks over here, right? So it might feel like we have a complete toolbox already. Like we have so many varied strengths, and each kind of problem can be tackled by its own singular block. But what we are not really like here's the catch basically, that each of these blocks also has some blind spots or weaknesses. So we saw models that are brilliant at pattern recognition, but can we really say that they understand those patterns? All they're doing is just like repetitively identifying those same patterns across thousands of images. But can we say that if we just shift the data slightly, can it still like identify that same pattern? So can it understand those patterns? Then we saw models that excel at capturing order and dependencies in data, right? But are they truly effective when the context changes very dynamically and very quickly? Or like there are very subtle environmental cues that matter, which you can't predict using like long-term context. We also saw models that learn through trial and error, the reinforcement learning block, right? But can trial and error learning alone be stable enough when the data is limited? Or when the stakes are too high? Can it still perform as well? We saw models that reason through logic and rules, but can strict rules handle like raw, messy, unpredictable data that doesn't fit neatly into the categories or like these rule systems that we just made. So basically these questions tell us one clear story, that no single approach by itself is enough. To handle the full complexity of real world problems, we need these hybrid architectures which combine the strengths while covering for the weaknesses. So in short, what are hybrid architectures? Uh, we're not talking about like inventing a new paradigm of AI over here. We're just talking about systems that integrate these building blocks that we've already discussed. So it's a thoughtful combination and it's highly dependent on the type of problem that you want to solve. If you see these two images over here, that gives you a very clear idea, right? So you have over here users who are tweeting and you want to do some sentiment analysis. So the way that they go about here is that they extract like features from like images in tweets, and they also extract like context using RNNs and then fuse them together to create a sentiment analysis, which intuitively, if you think about, will be much more accurate than just relying on one of them, right? You also see in the below picture over here, physics informed CNN being used with the convolutional neural net. So you can use like these scientific knowledges to really integrate that inside a normal CNN task. And this is for like a medical field. So you can use that scientific knowledge to give better simulations that maybe a CNN by itself might not be able to do. So let's like reinforce this point clearly with an example. The block diagram over here you see is like a system that it's followed in autonomous vehicles. So on one side you see image inputs that they can be like from cameras or LiDAR sensors, and they give us the spatial perception that we just talked about. On the other side are the symbolic AI. So this is the traffic rules, for example, right? And this provides logical reasoning. So we know the individual strengths of both. One excels at seeing, the other at reasoning. But when we combine them, we actually get something even more powerful. We get a system that's more robust as well as more explainable. And this is where the gains of hybrid architectures come from. The three gains that I think of: generalization. So, like in that same example, if the system can adapt across different cities, different weather environments, road layouts, and this it can do by blending perception with some rule-based reason that is consistent across all these environments. Explainability, right? So we have these rules defined. If the car stops at some point, we can point to the exact traffic rule that triggered that decision, maybe, or some other kind of rule system that we already implemented. Lastly, robustness. So even if our perception model is uncertain because the environment is occluded, right? The reasoning module still gives us a safeguard which reduces the chances of catastrophic errors. So I hope that using this example, I have reinforced this idea that hybrid architectures solve problems in a way which the individual blocks cannot do. Any questions till now? Yeah, that's a good question. We'll actually come to that as like a challenge as well. There's like limitations with resources, but also I told you about the type of problem that you want to solve. It's like unnecessary wastage of resources if you are combining all of them and the problem does not require that. So basically trying to think about what kind of blocks you want for what kind of problem is what we are focusing on. Anyone else? Oh, Do we also have a question over here? Sure, we'll get the lecture. Yeah, lecture recording will be provided at the end. Yeah. All right. Moving forward, now I'm going to talk about the design methodologies. So the question he talked about, right? Like, why not combine all of them? What are the design principles that you want to engage with while forming these hybrid architectures, right? So the first one is data fusion. And this is basically all about combining different signals in the pipeline. So I'll give you an example of healthcare diagnostics over here. Uh, so you see in the block diagram, the first level of fusion is data level, right? So at data level, you fuse raw signals directly. So for instance, if you have some pixel data from an MRI and you have some raw waveform data from ECGs, you combine them at the start and then feed it to one large model. This can preserve like maximum information, but it's very messy and computationally heavy, as you might assume. The next type of fusion that you can do is at the feature level. So you process each modality first. So an MRI goes through a CNN, for example, an ECG goes through a temporal model, for example, and then you fuse the resulting embeddings. And now you're working with these compact representations rather than the noisy data. And this is basically the strategy that's used in multimodal AI a lot as well. And then at the decision level, you let each model make its call. So if, for example, one of the model predicts cancer from imaging and another from genetic markers, you then fuse their outputs and let that kind of representation decide the conclusion of it. So the point here is that the time the time at which you fuse is not a one size fits it all solution. It really depends on what you value most in your application. And this can be between accuracy. So if you want to focus on accuracy, you want to focus on interpretability, or you want to focus on efficiency. The other design method, yeah. Yeah, so I talked about like accuracy, interpretability, and efficiency, right? So if you want accuracy, for example, feature level is the best bet for that because you are working with just the meaningful representations rather than like the full noisy data set. If you want like to ensure that like you work with just one singular model, like you have less resources, for example, or something like that, then you want to fuse it at, or like for any instance, you don't have a multimodal capability. You want to fuse it at the data level so that you can work with just one model. And if you just want an efficient a model which is interpretable, right? So then you can focus on decision level fusing. So that's the kind of framework that you can follow over there. Yeah.
Figure out of like when you say that you get more accuracy in the future level versus like computability in the early level, has there been like testing of this or has this been just like an accepted practice?
That's a good question. This is what I don't think so. It is still a research question. It's not something that's sure. This is just intuitively, if you think about it, I would say that that's what you would might do. But it's still a research question for sure. Yeah, it's one of the frameworks that you can follow. Yeah. The more hybrid architectures you have, the better it. So, like you mean like the more inputs you have, the better it would be. You're saying that. It's not necessary that that's the case. Actually, sometimes that even complicates the problem further because you have more representations to like pass through or like embed, right? So that does not necessarily guarantee that you'll get more accuracy. Yeah. All right. Moving forward, now we're going to focus on the model design itself. So the challenge here is again which block to connect, right? Like just knowing what the block is not enough. Like focusing on the problem you have and then trying to figure out what kind of blocks you want. So I have four kind of points over here that you can like kind of see. The first is identifying complementary components. So this is heavily dependent on the input or output you have. Uh, and what kind of strengths do you want to combine? For example, if you want perception with symbolic rules for reasoning, like we saw in autonomous vehicles, which requires that explainability as well as like perception, that is where you'll use those blocks together. So it really depends on the output you're looking for and the inputs that you have. Second is, like we talked about, choosing the integration level. We covered that already. Third is having these priors and constraints, like physics informed constraints that we had, or like domain knowledge, or these rules. So like if you want to or don't want to infuse them, depending on the problem. And finally, we can follow a modular design pattern which is reusable across problems. So like, for example, you see on your screen a generic hybrid framework. Now, which block you want to use from this? You have your perception, you have your knowledge priors, you have a fusion layer, and then you can either get the output from that, or if you want some reasoning added to it, you can use that block as well. So it's very like flexible in what kind of problem you want to solve. All right, now let's go into transformers a little bit and get a refresher about what transformers are, right? So BART is a really nice example of a transformer which combines a strengths of both an encoder type and a decoder type in one architecture. So on your left side, if you see, you have that encoder stack. So the main objective there is to understand the input sequences. If you go deep into the architecture itself, each layer has a multi-head attention and feed-forward blocks with also like residual connections, as you can see over there, and some normalization also added. So what this does is it allows the model to capture context in both directions, and it's able to pay attention to the whole input at once. That is the strength of the encoder stack. On the right side, you can see the decoder, and it looks very similar, but the key difference is the masked multi-head attention in the bottom block over there. Uh, so that focuses the decoder to only attend to previous text rather than the future ones. So the main task over here is for it to generate text one word at a time. So that is almost like what you'll see in like a GPT model. And this is the not a chat GPT, this is like GPT model. It's at a different.
For now, we know that we have not covered all of this in the beginner workshops, but we'll be going over all of this. So for now, take this with a grain of salt, and we'll be going over it in the beginner workshop as well.
So the real power of what BART is that it combines both the encoder and decoder. So you feed in some input text, like you have a noisy sentence or a long passage that needs summarizing, and the encoder first builds a deep semantic representation of that input, and then the decoder takes that representation and generates a new output sequence. So this can be, for example, a cleaned up sentence, a summary, or even a translation. So let's move on to a very important architecture that we're going to focus on in our hands-on as well, which is CLIP. And CLIP is basically at its core, it takes very different inputs, images and text, and then learns to embed them in the same embedding space or the same space. So that means if you take an example of a black cat on a sofa and the caption, a black cat on a sofa, they both end up as vectors that live close to each other in this shared space. So both the text and the image are close in embedding space. So in short, why is this powerful? Why do you want this? Because you've got everything mapped into a same space. So you can reuse that embedding for different tasks, like for example, a recommendation system. So if you like an image of a cat, the model can pull some nearby similar images of cats and recommend that as an option. Or you can also think of using a decoder only LLM. So you can turn those embeddings that we got and generate some captions, or even you can use it to question answer about the images itself. We'll also see later a technique called attention pooling, which lets us reduce the complexity of these embeddings. So instead of treating every pixel or token equally, the model can learn which part of that sequence matters the most. And yeah. So moving forward, let's keep this example in mind that we have our black cat on a sofa image, and also we have its caption. And I'll walk through how each step goes through that. So first, let's start with like the pre-processing, right? So we have our images and text, and like we have them and they're not in the same space, right? So we first need to pre-process. So if you look at the left side, which is the image slide, over here, like this is like a error over there. All of these should be image embeddings. Um, so the model over here basically doesn't see the whole image. It basically first parses it into some patches, uniform square patches, and then each patch is flattened and passed through a linear projection layer to become an embedding vector, which are those image embeddings that you see in the architecture over there. But we cannot stop at that only, because we also need to add what's called positional embeddings, because a transformer is not aware of positions in an image. So when we add these positional embeddings, for example, the model knows that this patch is top left, this patch is bottom right, and then you can reconstruct the whole layout of the image. Then on the text side, we have our caption, black cat on a sofa. This is simply broken down into tokens, so literally like word by word, a black cat on a sofa. And then each token is mapped to an embedding vector using an embedding table. So just like with images, we also add positional embeddings over here. And the positional embeddings over here, what it does is that it lets the model know that the word black or the token black comes before the token cat. And without that, we wouldn't have any order. So that's why the importance of positional embeddings is over here. So by the end of this pre-processing step, we have both our inputs, image and text, turned into ordered sequences of embeddings. And this sets up nicely for the next step, which is to send them to their respective transformers. So you see on the image side, we have these sequence embeddings. This is fed into a vision transformer, or VIT, and VIT applies self-attention over the patches. So each patch embedding can attend to all the other embeddings in the space. So for example, if we have a patch that covers a cat's ear, for example, and another that covers a patch of the sofa, both of them can be connected, and like the context is there. And so you can have a global understanding of what's in the image. On the text side, you have the token embeddings. They are sent into a transformer encoder, which is similar to what you saw in BERT. BERT was the encoder part of the BART architecture. So over here, again, self-attention allows each word to consider the others in context. So the model knows that black is modifying cat, and that sofa is the object being referenced. And at the end of each encoder, we actually don't keep the whole sequence also. We actually pool them into a single vector for the image and a single vector for the text. So these are then compact representations that are able to summarize the entire input. So important point here still is that we still have the image and text streams completely separate. So we're not doing any combination operations over here. Any questions, Phil? Yeah. Embeddings, you can say.
Technically, there is no difference. They are just vectors, what we pass in through the encoder layers. Yeah, overall there is no difference in that.
Yeah.
Is add of the text both into the same vector space or they're like separate vector space?
So eventually we want to have them in the same space. Yeah. But that, yeah, they are being processed separately. If it's in the same vector space, do we call it as a multi? I didn't get your question actually. So we are not combining them. We are like, eventually we'll come, you'll see that soon that we're not combining them actually. We're just putting them in the same space. Yeah.
So like, for example, like you had just trying to generate a graph, right? But all of the vectors of the image and the text are the same. And so how would the vector exclusion know that, okay, I need to get a text space vector or not an image space vector? Because this is just simply all of the
Yeah. Do we want to do it right now? I've not covered that yet. Yeah.
Oh, yeah, he'll be covering it in some time.
Yeah.
Like it's the next part. You'll get it.
Any other questions?
Until now, what we have done is we have just like created vector representations of our image inputs and text inputs. Now, next we'll see how we combine them or like align them in the same vector space.
All right. So like he mentioned, now the next step is projection. So Clip has like a lightweight projection heads on top of both those encoders. And what they, in like simple terms, do is that the pooled image vector that we had and the pooled text vector that we had, it's but just like put in the same embedding space. So at this stage, the image vector and the text vector are just in the same space and they can be compared to each other. They're not getting combined still. That because that's not the scope of this architecture. So we can have direct comparisons between them right now, since they are in the same space over here. So now let's come to the actual part of it, which is basically what Clip does at its core. So now we have our image embeddings and our text embeddings or text pool vectors are in the same space, right? This what you see over here is similarity matrix, where each row is representing an image and each column is representing a caption or a text. And at the intersections, we are computing some similarity using a dot product. So if to best show this, I'll give you an example again. So we suppose instead of just one batch that we had, the black cat on a sofa, we now have four. So we have a black cat on a sofa, a dog catching a frisbee, a car stuck in traffic, and so on. So, and the same for captions also with those images. Now, this matrix is built by comparing every image with every caption. And the ideal outcome is that the correct pairs, a cat with a cat caption, a dog with a dog caption, and so on, are going to appear on the diagonal over there that you see. And each of them should have the highest similarity scores compared to the off diagonals, which are representing, suppose for example, a cat image with a dog caption. So the training objective is what's called a contrastive loss, and it basically pushes that diagonal scores up and pushes the off diagonal scores down, which is exactly what we want over here. And over time, the system learns the joint embedding space where images and captions that belong together are actually also neighbors in that space. So that's how you are able to retrieve some other caption. So I hope that makes it clear as to how exactly we're doing the retrieval process. And the key thing over here is that this is not done in isolation also. So we have like multiple batches together, and yet it's able to learn this kind of system where the same image with the same caption is close in that space. So before we move on to the hands-on, I quickly also want to introduce an extension or like a process that we can use with Clip, which I talked about, which is attention pooling. And to like simplify what attention pooling is, I'll just quickly explain the terms in it. Attention is the mechanism which lets a model see like different parts of the input. And pooling is basically averaging all of them together. Attention pooling is like combining both of them together, where instead of averaging blindly all these inputs, you are actually averaging those weights that highlight the most relevant parts of the sequence. So if you, for example, in our cat on sofa example, the patches showing the cat are getting more weight than the background. And if we think of the caption, so words like black and cat matter more than the rest of the filler words. So with that, I think so we'll move on to the hands-on. Sure. Actually, before the hands-on, we can just focus on like the rest of the theory content so that you guys get clarity of that. So extending to Clip, we are now going to talk about VLMs. So VLMs, the first pattern of VLM is built around the idea of unified embeddings. So over here, an image is passed through a VIT, which is generally the vision encoder of choice, and then it is projected into a frozen LLM model. So like a GPT style decoder that generates input or generate text, sorry. So the key idea here is modularity. I've given you some examples like Blip2 over there. Over there, the image is converted into embeddings, and then it is projected into a format that a frozen LLM can use to generate text. And Lava works very similarly as well. So the one key strength of this approach is efficiency. So you don't have to retrain the LLM. You can just reuse a powerful pre-trained model and just learn the projection of images on it. But the trade-off is also critical. If the projection doesn't capture all the features, then the LLM can't do anything about it, right? So they really depend on the quality of the projection step over there. The second pattern of VLMs is the Flamingo type, and the only difference over here is that we insert special cross attention layers into the frozen LLM. So basically there's a query system over here where the text tokens are able to query those image tokens. So you can selectively focus on parts of the image while you are generating the text. Yeah, and like the trade-off over here is complexity. Cross attention models are more powerful, but they are also heavier to train and more demanding at inference. So I want to end this part with just some challenges and open questions that I think of. So in hybrid architectures, one is balancing accuracy and interpretability. So often the most accurate models are also the least explainable. Um, and hybrids needs to carefully trade off between the two. So like what kind of like blocks you use is very dependent. Training stability is also a problem because you when you combine, like if you want to combine very different components like symbolic rules and physics informed, if you ever want to, for example, then optimization can become very fragile. Another challenge is scalability. So a design that works in a controlled research environment does not guarantee that it will translate to large scale. There's also the problem of benchmarking across domains. So we don't yet have like standardized frameworks to compare effectiveness in different industries for hybrid architectures, since it's still a resource problem. And finally, there's an issue of data availability also. So to really train like diverse multimodal data sets, you need access at scale, which is not always there. So with that, before we do hands-on, if you have any questions, just let me know. Yeah. Clip by itself is not generating anything. Clip, and you add a decoder on top of it, it can generate text. Clip is just giving you a joint embedding space where you have image and text pairs. But compared to VLM, where like you are actually feeding images tokens into a LLM also. So over there, it's kind of a unified embedding space like we saw. Kind of, yeah.
Yeah, pretty much. So the encoder of any kind tries to understand what is being fed, the inputs basically, and the decoder is the one responsible for generating text or anything for that matter.
So basically, so like are you familiar with the process of benchmarking in general, or like, so benchmarking is basically so comparing to a reference point. So you have some standardized or like some benchmarks which are universally accepted in that field, and you want to compare it to that level so that you can say or like prove that your concept is working. So that is something that's still not there. That is by itself a research problem actually.
Are you aware of the ImageNet dataset on which the traditional models for computer vision are trained on, like the ResNet or VIT for that matter? Yeah, so and they also have a standardized metrics like which are used to compare different models on. So the data set remains the same, the metrics used to calculate remain the same. Now the your model changes, so in order to compare two or more models, the metrics are important because they tell you like which is better, which is worse in certain scenarios. That is the process is known as benchmarking.
Yeah, and we don't have that in like multimodal architectures. Like we don't have a standardized data set like that for now.
But not in all the
Hmm.
all.
Yeah.
Are these challenging across all hybrid combinations, or is this limited to specific hybrid combinations? Because there's a lot of like diverse challenges here, and also like you define hybrid as scalable, like symbolic plus LLM, for example. Does that have the same problems as just a multimodal LLM in the context of these ones?
Yeah, these are not generalized across all. This is like specific. So it's not generalized across all the hybrid I said. Yeah, this is kind of, yeah. Because I feel like what I came up with this in lecture, like hybrid architectures are not essentially what like I talked about. It's like it's like a kind of framing. So it might be confusing slightly that when you talk about hybrid architecture, you might think of multimodal, but this is another viewpoint that you can follow maybe. But this is a good question actually to clarify. These are all challenges in multimodal research.
The best example for this is like AlphaFold. It is a biological thing, like it's a model which is used to predict protein sequences, the shape of them. So that may have some challenges from this, but not all, as compared to like the VLMs that we talked about. So they are like the hybrid architectures are the superset, and multimodal are a subset of that.
But the definition of hybrid architecture, I believe, is still like questionable. Any other questions? All right.
You guys can also code along with us if you want. We'll be starting in like 1 minute. I'll set up my laptop. Yeah.
Hey everyone. So we'll just take a 5 minute break. In the meantime, we have a person from Anthropic. They have some things to share with everyone today, so I'll hand it over to them.
You could put the first slide. Yeah. Hi, everyone. My name is Shavain. I'm the Claude Builder ambassador for our school. And so we're here today and we're going to be here for the next like 6 to 7 weeks, basically promoting Claude across campus, offering students with 6 months of free Claude Pro and $50 in API credits. And this is unlimited. I also have some merch for you guys if you want some. And so we're going to be hosting end of the year hackathon with I think it's $500 in API credits per winner and $500 in prizes. And so there's going to be a no code track, there's going to be a builder track, and many more. And we're also going to be partnered with many clubs. So you guys might see me at future events, maybe with like Google developers or Soda. So can you go to the next slide? Yeah. Yeah, so if everyone can sign up for the form, so this takes it to our website. And on the website, if you click join us, you have to fill out a form with your ASU school email. This will essentially sign you up for the club. But this is one of 2 parts. So the second part, in order to receive 6 free months of Claude Pro and $50 in API credits, is you need to attend a virtual meeting that we have on Saturday, this Saturday from 1 to 2 p.m. You're gonna have to fill in a check-in form at that meeting. And only once you fill in both the sign-up form and the check-in form can you get like all of the benefits. If you just do one of the 2, or if you don't do it in the proper order, you're probably not gonna get everything that you need. I'd also highly recommend that you join our Discord, which is in the website. It'll give some important information if you have any questions. Yeah, no worries. And yeah, so we're gonna be here on campus. You can reach out to me. My name is Shavain. I think my GitHub's on the website too at the bottom. So like you guys can reach out to me if you have any questions. And you can come up and get some merch too. We have tote bags. I don't know if you guys like that. Tote bags. We have sharpeners, pencils, and we have a couple of hats. We don't have a lot, so yeah, come here and like take them if you want. Oh yeah, for it. Oh, you want a hat? You can give it to okay, just take it now. People, yeah, take whatever you want. Don't take all the pencils. Please don't take all the pencils, and don't take all the sharpeners too. Come on, come on.
Guys, it's 1 per person, right? 1 per person. Guys, it's 1 per person.
Become the ambassador.
Everyone scan the QR code. Is anyone yet to scan the QR code? Okay. If anyone wants to talk to him, please feel free to. We'll take another 2 minutes and then we'll get started with the coding.
All right, any final questions? All right, great. Yeah. Yes, it will be during Sun Hacks if it's from 1 to 2 p.m. But you can just like be there like on the meeting on the side. You know, there will be a check-in form. Yeah, hopefully you guys will be able to make it.
All right. We'll get started with the coding session for Clip now. I'll hand it over to Bhavya, who will be doing walking you all through the code. So I hope all of you have your laptop with you opened up so that we can get started with the coding.
Keep it on my back. So. Okay. Oh, can you guys hear me? Yeah. Okay. So what I'll first do is we'll copy the okay. Where's the link? Mike? Okay, so today we'll be going over this data set. It's a VQA data set with just visual question answering. Uh, we have three columns. One is the image, which will be the input, and the question, which will be the textual input that we will be feeding into the model. And these are the true answers that we expect our model to get. As you see, like it's a medical VQA. It has some MRI images, X-rays, and stuff. And we expect the answer to be some kind of a textual output. Uh, yeah. So this is a code that I'll be using, and I'll be going over this as well. So yeah. If everyone can just open their Colab notebooks. So first we'll be using the GPU runtime since large language models are huge and require GPU computation. So you can just go to your runtime, change runtime type, select the T4 GPU with everything else remaining the same and just save it. Just let me know once you guys are done with that part. I can move on. Is everyone good with that part? I'll move on. Cool. So now we'll be creating a vlm.py file. So basically the issue with um, Colab is it's a notebook environment, so we cannot directly run Python files as is like we do in VS Code. So we'll be saving the vlm.py file as a code, and then we'll be running it from our Jupyter notebook. So to you can start with clicking this terminal, which will take you here. Once you do ls, you will see that this is the initial directory that we have in our workspace. And then we'll be creating a vlm.py file using this command, touch vlm.py, and you can see it in this sidebar being created. So once you have this, we can copy and paste the code that I'll be discussing soon. Uh, Next, in our Jupyter notebooks cells, we'll create a first cell with cd /content. The brackets matter here because this is a Linux environment. So we'll be changing our directory to this directory that we have open in our sidebar. Then we like don't need the sample data directory, so I'll be removing that. Next, we need to configure Accelerate. Accelerate is a Python library which we'll be requiring to leverage our GPU. So to install all of the libraries, what we'll do is we'll do pip install Accelerate transformers Peft. Uh, yeah, I'll close the site terminals and you can Peft. Then there is bits and bytes. Uh, we need data sets. What else do we need in our code? Oh, of course, we need Torch. Uh, so the best way to install Torch is to go to PyTorch, getting started. We'll do all of this. So stable, since our environment is Linux, we'll be using pip to install it, Python, and let's say we want CUDA 12.8. So we just copy this command and we can paste it in our collab. So it will be Torch, Torch Vision, and yeah. So these two libraries will be installed on. Uh, yeah, I think pretty much that's it. Uh, good. Okay, now let's dive into the code. So initially, when our code, we start with the parse args function. What it does is it basically accepts the command line arguments that we give during execution. So the command line arguments are important when we want to define some parameters during runtime, uh, which we want to configure on the go. Like it could be the model name that we want to use. It could be the LLM model, the clip model, or the data set that we want to extract our data from. It can also define the output directory where we want to save our model, the number of epochs we want to train our model on. So from here on out, the hyperparameters start, as you can see. We have the number of epochs, which is like how many times we want to pass our training data through the model in order to make it train. Then we have batch size, how many sets of images or samples do we want to pass in one go. Then there is learning rate, which is an important parameter, hyperparameter. It controls the training speed, or rather, like the speed of convergence. If we keep the learning rate too high, it overshoots the uh, local minima, and yeah, the error may increase. Then we have max sequence length, which defines how many maximum uh, tokens we want in our input. This controls how much of the GPU memory we'll be using, because like in the transformers, this is one of the hyperparameters. Then since our GPUs on Colab as well are not that powerful, we'll need to quantize the model. Quantization, we'll be covering it in one of the future deep dive lectures, in I think model optimization. So yeah, so basically quantization just lowers the memory used by our large language model. Then we have quantization type, which is the subtype of that. Then should we be using mixed precision? Again, this is a model optimization technique. We'll be going over that as well later on in later lectures. Precision type, same uh, use case. LLM train strategy. Even this is something that we will be going on. So there is LoRa, freeze, and full. So we can choose one of these methods. LoRa is like we are training a very small number of parameters. Freezing is we are not training any parameters in the LLM. We'll use the LLM as is. Full means we'll tweak every parameter in the LLM model, which can lead to a lot of memory constraints. Like it'll take a lot of our memory. Then we have clip training strategy. The options are the same. We can use LoRa, train a few parameters, freeze, not train at all, full, train the whole model. Projection train strategy is for the projection layer. So let me just go back to this. Okay, let me go over this first. Then these are the hyperparameters for LoRa. So if our LLM train strategy or clip train strategy is LoRa, then these will be activated. Yeah, so these are pretty much the arguments that we can pass to our model. Now to go back to our slides.
Let's take a pause. Does anybody have any questions regarding the parameters or any other thing?
Yeah. Oh, so I'll configure it for you in some time. So don't start with the configuration right now. Or any other doubts regarding the command line arguments? Cool. Oh, yeah. I'll be publishing it on. Yeah. For now, I'll present it, and if you want, you can copy, and later we'll be sharing it on Discord and other places. That's fine. Cool. Okay. Okay, let's do this. I'll share this with you guys, and I'll write the code here. Oops. Guys can take a picture for now. We'll quickly move on to the. Let me know once you're done. Raise of hands or like thumbs up would be nice. Oh, are we good? Okay. I'll move. Cool. So where are we? Okay. I think viewing the code here would be better than the commented part of. Yeah, so we set up logging as well. So logging basically tells us like if there are any errors, warnings, or any logs that the code gives us back in order to know like our model is facing some issues or is some training going well and stuff. Cool. What I would like to start with is the main function because that will make the task go first. Let me just share like what we are going to be going over the hands-on part. Cool. The hands-on part we'll be going over uh, the unified embedding decoder architecture. So we'll be doing this first part of the architecture wherein we have an image input which will be passed to the LLM, decoder LLM, but first it will be passed to the VIT, sorry, the clip encode, image encoder, and we'll be getting these context vectors out. Also, we'll be inputting text input, which will be the question that we saw in our data set. And yeah, these two will be passed as a single input as embeddings into the decoder LLM. This will be like a GPT-2 encoder, sorry, decoder, and we'll be generating text, which will be the output that we are looking for. I'll be referring back and forth in order to explain the various components that we'll be building. Okay. So initially, this is the accelerator that object we need to create in order to leverage our GPU. It takes in some arguments like mixed bit precision that we already defined in our arguments, as you can see. So args.anything is something that we are referring in from the command line arguments. Moving on, we set up a tokenizer. So remember the LLM model name that we are using, which is OpenAI's GPT-2. We are creating a tokenizer for that LLM model, which will encode the text that we are passing as input and also decode the text that we will be generating from this model. Okay. So next we set up padding. Padding basically takes care of the length of the input. So as you know, sentences can have variable number of tokens or words. So in order to bring it to the same length, in order to pass it to our LLM model, we do some kind of a padding. So setting padding to the right means when we have a sentence, we pass in padding tokens to the left in order to make it to a certain length, which is specified by our max sequence length argument we define in the command line arguments. Next, we initialize the clip image processor. The clip image processor basically takes care of all the pre-processing that we need to do on an image in order to make it compatible with the clip model. So to pass it to the clip model. So here, assume that this is the image that we are passing through. So in order to even before passing it to our clip model, we need to do some pre-processing on it, which is taken care of by this clip image processor. Next, we'll be loading our data set, which is again passed through the command line arguments. And it has two splits. If I go and have a look, so it has like two splits. One is a training split and one is a testing split. We'll be using the training split to train our model. We'll be using the testing split as the evaluation that we do during training. Okay, I'll wait.
Can you increase the brightness?
Oh, sure. I think the brightness on my side is full. Let me just check it from this side.
Just change the light setting.
Yeah, I'm light. Should I do full?
Wait. Let me know when it's a little better for you guys. Better?
Okay. Sorry, guys. Okay, yeah. So we load the dataset in the dataset object, and then we pass the training split to our VQA RAD dataset class that we have defined above. I'll be showing that in a bit. So basically, what we're doing is we're creating a custom class which loads our dataset, which is in the dataset object format, and we are converting it into a torch tensor format that we can directly pass to our models. So let's move on to the VQA RAD dataset. So here, as you can see, it takes in some arguments. First, what it takes is the dataset that we want to pass, which is the Hugging Face dataset format. It takes in the tokenizer object that we created. It takes an image processor object that we created as well, and the max sequence length that we defined in the command line arguments. So once we have all of these with us, what we do is we go over each batch of samples in our dataset. So let's assume that we have a batch of samples which is indexed by this IDX argument, and in the get item function, we are reading the question column from that. We are reading the answer format from that. We are reading the image format from that. So as you can see, like these are our inputs that we are going to pass. So we are taking this out from this, we are taking this out and storing it into this variables. We are taking this out and storing it into a separate variable. Now we are processing the image that we have extracted using the image processor, which is the clip image processor that I showed you below. And we'll be, so we'll just pass it as this, and the return tensor is PT, which means that we want the output as a PyTorch tensor. Hugging Face supports PyTorch, TensorFlow, Z, and some other formats as well. So we need to define what we want as the output, and then we squeeze the pixel values that we get with the dimension 0. Basically, we are just reshaping it in order to make it compatible with our model. Cool. And if in case the image processor is not able to process any of the image values, we'll be passing a dummy black image. Cool. Okay. Next, we take in the question answer that we have in our data set, which is this one, and we encode it into a format which is like a user assistant format. Sometimes this is also referred to as like an instruction tuning, but this is more or less like a supervised fine tuning method, wherein we'll be passing the question at test time and we should be expecting this answer in this format. Okay. So once we have this is all of this happening on our dataset which has the true entries. So this is the ground truth value that we'll be passing here, and this is the question that we'll be passing at every iteration of the training loop. Next, we tokenize this whole prompt that we have in order to pass it to our LLM model. And it has some arguments that we need as well. It has the max length, which we defined from the command line arguments. We have truncation equals to true, which is actually I would recommend you guys check out the documentation. The Hugging Face has a else.
When you are tokenizing the prompt for the LLM, so LLM will be you tokenize it, or like are you just like putting your own tokens and then the LLM will just take it directly?
The LLM has its own tokenizer, so it already has a vocabulary set of tokens it has already learned during when it was trained. We are using that to encode this prompt that we are passing it here.
So it will again like go through the LLM's own tokenizer as well as like through this particular prompt.
No.
What I'm trying to understand is it like going to be, for example, when you are typing in ChatGPT, so it tokenizes whatever prompt you are giving. Here you are like taking a prompt and you are like tokenizing it by yourself. So I was trying to understand like whether then it's passed to an LLM in the back end, it will tokenize it again. So if you create a token set and then it is again like taken it by the LLM and re-tokenizing to a different like matrix.
Yeah, no. So, okay. So we are just passing this to the LLM, which already has a vocabulary with it. It does not know like we'll be passing this as an input. So this is going to be converted into numbers, and then we'll be passing it into the GPT model. So up until this point, we have a vocabulary of words, and this prompt will be token like it will be just converted to numbers. That's it, and that numbers will be fed into our GPT model. I hope I answered your question. Okay. Yeah. Sorry. Yeah, you can do it later. We'll have a talk if you want later as well. Okay. So we pass in our prompt to the tokenizer, which technically converts this text into a sequence of numbers. It can break it on subwords and stuff. Next, we even like squeeze this with dimension 0 again, reshaping it to feed our LLM. Similarly, the attention masks are also generated by this tokenizer, which are again squeezed in order to fit the input format of our LLM. Next, in order to generate our labels, we just copy the input tokens. So input tokens here are the whole prompt, as you see. And now we are recopying it as labels because the GPT generates text in an autoregressive way. So first it will take the token user, then it will output the first part of the question. Then it will take this whole part of the text and generate the third part of the sentence. So the labels are technically similar to the input sequence, only right shifted. The right shifted part is again taken care of by the Hugging Face library. We don't need to do that. Okay. So labels, and we pad the prompt length to -100. So during the calculation of the loss, we don't want our model to generate the question that we are putting in, because the question can vary, but the answer should be relevant to what the question is being asked. So we, in order to not calculate the loss on the question part of the prompt, we'll be um, we'll be replacing the tokens of the question with -100. Yeah, moving on. And the rest of the part again will be padding it. So the padding also should not be predicted by our models. That's why we are the indexes which have a padding token, we'll be replacing those with -100. Finally, this is what will be passing to our architecture. This architecture basically. So now let's compare it. Pixel values, which are technically what we'll be passing it to the clip model. We have not parsed them yet, but we'll be passing them, and they will be looking somewhat like this, but clip will align them to what the GPT can understand. Next, we have input IDs, which are the text tokens, but in a numerical format. We have attention mask, which is also used by a GPT model. Actually, for the beginner people, we covering all of this in the beginner workshops in the later. So for now, just hear me out. Labels is what we'll be comparing our GPT generated code with, GPT generated tokens with. Cool. Okay, let's move back to our main function. So up until now, what we did was we just loaded the dataset into a format which can be accepted by our CLIP and GPT architectures. Similarly, we do the same thing for the text dataset or the validation dataset here, since we are using it during training. Next, we have a data loader object. So in PyTorch, these two objects, one is the dataset object and the data loader object, are both used simultaneously in order to load the dataset into the model. The data set object loads the dataset in a specific format, whereas data loader is responsible for feeding the data to the model, any model for that matter. It also takes in this dataset that we used here, and we give a batch size, like how many batches do we want to pass in a single go. Okay. Now we have our data. So we can move on to building the model architecture. So this model object here is the whole model that we are looking for. It contains the clip, it contains the projection layer, it contains the GPT LLM, which is basically this whole structure right here. Okay, so this is a custom class because all the three components are independently created. Like two of them are from Hugging Face. The projection layer we are building it using core PyTorch. So this is a custom class that we built. So let's go over it as well. We define this class as an NN module, which is a standard module that we use to in PyTorch to define any component for that matter. It takes in some arguments like the clip model name, the LLM model name, use quantization by default, which is false, the quantization type, which is 4-bit, which depends whether you use quantization or not. But all of this is passed as a command line argument, so we can move on. Here we define the clip vision model, which is a class given by Hugging Face. And we take from pre-trained, it means we load the weights which were trained with like the original clip weights that we got from Hugging Face. Next, we define a quantization config. So again, this is a way to reduce our model's weight. So we define a quantization config depending on if we have a use quantization argument as true or false. Next, we move on to the LLM. So this is the part which loads the GPT, only GPT-2 part of the model that we are trying to build. So here we get the GPT-2 model here, and it also it gets the quantization config since we want to quantize that part of the model since that's a large one. Then we have the projection layer that we built, which takes in the clip's hidden state as the input, and also the LLM's hidden state that we want to pass to the LLM. The next part is the forward method of this init.module. It defines the forward pass of our whole model, like passing the image inputs to the model, passing the text inputs to our GPT model, and the whole thing up until generating the text tokens in the output. So just to go over it very quickly, we have the pixel values that we get from our data set, from our data loader, sorry. Then we pass those processed pixel values to the clip model. We get the image outputs. We do this with no grad here because we in our command line arguments, if you must have seen, we have a argument which says clip train strategy. Here, clip train strategy, when it is set to freeze, we do not pass the gradients back, which means that the model is not being trained. We are freezing the weights. Okay. Moving on. Okay, so that was dependent on how we have the command line arguments. But if the command line arguments say that we want to train the full model, we'll pass the gradients back. Next, we take the output of the clip, which is of the shape backslice, comma hidden size, and we pass it to the LLM, which is taken care of. My bad. So yeah, the output from the clip model is passed through the projection layer, which is done here. The middle part is just like reshaping and stuff, and making sure that we don't get a NAN or something like which does not have a computable gradient. Next, we pass our clip out context vector to the image projection layer, and eventually we clamp some gradients, and we make sure that the values of the vector are between some values and stuff. And then we pass it to our LLM right here. So this is where we start with the text embedding. Actually, yeah, my bad. So we combine the image and the text embeddings like in a similar way, wherein all of them are passed as a single input to the GPT model, rather than separate like one pass you pass the image inputs, one pass you give the text input. Instead, we pass both of them in the same forward method. Hence the get input embeddings. The image embeddings are concatenated with the text embeddings here, and we pass the input embeds to our LLM model, which is right here. Now, once we have passed all of this, we get an output. We calculate what is the output loss based on the generated predicted output and the true output. If the loss is like an NN value again, we discard that and we take the next function. We set it as a constant tensor of 5.0 if the loss is like infinite. So 5.0 is a small value as compared to infinite, so we set it as that. Apply training strategy. Yeah. So this is where we apply the freeze, LoRa, or full training to each of the model components that we talked about. Moving on back to our function. Okay, we did not talk about LoRa, my bad. But yeah, so we have a model as well now. So passing the input directly to this model will give us a set of outputs. Next, we have LoRa, which is again something that we'll be covering in future lectures. But for now, just assume that a small amount of the weights are trained, and we need to once the model is defined, we need to do it after that. So PFT takes care of that. So various components we apply training strategy, giving the LoRa configuration respectively, like LLM LoRa config, clip LoRa config, and stuff. Okay. Next, we define our optimizer. Any deep learning training requires an optimizer. Here we use Adam W, which is the weighted Adam, I believe. It has we pass in the learning rate that we want, with which is passed on the command line arguments, and we actually reduce it. So whatever the user says, we give only the 10% of that. Because we are also defining a schedule. So during during the training of these LLMs, we need to initially increase the learning rate and then drop it for a stable gradients and training. So this is also something that we'll be covering in some of the other lectures. Next, the accelerator.prepare takes care of passing all of this to the model's GPU memory. All of this up until this point was on the CPU memory. The accelerator.prepare passes it to the GPU memory because we want all of our components there, because all the calculations would be taking place there. So the accelerator.prepare takes care of that. We don't need to manually do two-day wipes and stuff if you are aware of PyTorch. Next is the training loop. The training loop is pretty standard. Let me just summarize it in a few steps which are crucial. So we pass through all the data that we have from our first we iterate through epochs. So we'll be defining what we'll be doing in each epoch and then looping over that. So initially we set the training loss to be a 0. Then we'll be parsing over the train data loader that we defined above, which is somewhere here. Yeah, right here. So the data loader will be parsing over that. We'll be taking each batch from that, batch ID, batch, and then we'll be resetting our optimizer to 0 gradient. We need to do that at the start of every epoch because we don't want to use our previous loss in order to know the current loss. Next, we take the whole batch, we pass it through our model. So like I said, we already have the model, we just need to pass the data. We don't need to do any kind of processing or anything else. We can directly pass it to our model in this way. The star star basically is it is a separator which passes corresponding arguments to the model object. Next, we compute the loss from the outputs that we get from our model, and we backpropagate that. That is taken care of by accelerator. So initial torch models, traditional torch, if you use it, we do loss not backwards. But here, since everything is on the GPU, and when you have multiple GPUs, tracking the loss becomes a real issue. So accelerator again takes care of that. We don't need to worry about how the loss is propagated through different GPUs. Okay. So let's go over this very quickly. I'm in the last part, and since you guys have the code, you can refer it back. Yeah. Now we have propagated the loss back to our optimizer, and now we need to step up into the in the direction where our loss is being reduced. So we do this by optimizer.step, which takes our model into the direction of a lower loss. We also reduce the learning rate because we have a learning rate scheduler here. And we add the loss that we got to our total loss in order to know how much loss we are at a given epoch. Finally, we go to the evaluation loop, evaluation part of the model, wherein we pass a batch of data to that, and we do the same steps, except we don't pass the loss back. Because this is not the training data, we are not learning on the validation data, so we don't pass the loss back here. So everything remains the same except the accelerator backward component and the learning rate step and optimizer.step part. With this, I think we are done. We have a training complete. So this code works apparently. I tried it on my machine and it works. So You guys can try it at home anytime if you guys want. Let's share it horizontally. We'll also be sharing it officially on our channel and website, I think. Yeah, that's it for today, I guess. Thank you guys. Oh yeah, any doubts?
So I know there's a standard atom and there's an atom W.
Between Atom and Atom W. Atom W is a weighted optimizer rather than the traditional Atom. If you must have used that. I'm not sure about the specifics today, but if you just read the paper or just ask GPT, it would give you that. I don't know the exact specifics, but I believe like this takes in the previous gradients as a weighted, like attaches weights to the previous gradients and tries to use momentum, I believe. Yeah. Yeah.
So in that architecture that you showed, there's a section called option.
Oh yeah.
Not clear. That's the
Image, right? Okay.
Oh,
This one, right? Yeah. Dropout is we use it for regularization where we make the weights of like some of the neurons in the multi-layer perceptron that we use to zero. Like we basically make the network generalizable by telling it that this time you are not using some of the neurons, you are using the other neurons. So basically the gradients pass through all of them and the model does not only use a specific number of neurons to get the output. Yeah, that is done randomly, yeah. Any more doubts? Okay. I think we'll meet in the next workshop, which is on Monday. Stable diffusion. Cool.
For the image, we have to convert image into binary data, right? For the input.
Not binary data. We normalize it by dividing like I don't know the exact steps what Clip uses, but
Okay.
usually
You have
we
directly to give to clip, right?
the
Clip.
processor part, yeah, it takes care of that. We don't need to manually know what's going on. Like you should know, but we are not manually controlling that part out. Yeah.
Yeah, I feel like I'm more on the beginner side. I understood a little bit of what you were saying.